try to solve this problem here. What we have is Cauchy's linear differential equation here. Okay, now we can write this as x square, this is d square into y minus xd into y plus y, which is equal to 2 log x. Okay, now further let us try to solve this. Now if I take y as common, so I get x square d square minus xd plus 1 into y, which is equal to 2 log x. Okay, now let us put, that is log x as z, so that or we can write that as x is equal to e to the power of z. Fine, and then afterwards let us again substitute these elements, that is xd as d1 and x square d square as d1 into d1 minus 1. Okay, now let us substitute those which I have mentioned here. So I get this is d1 into d1 minus 1, okay, d1 minus 1 minus d1, okay, plus 1 into y. Okay, that's what I have done here, as I have substituted for x square d square and xd and 1, which is equal to, now this is on the right hand side you have 2 log x. Log x can be written as z, so that is 2z. Now when I try to simplify this further, so I get d1 square minus 2d1, right, plus 1 into y is equal to 2z. I hope you have understood this. Now further, now this is an ordinary differential equation of second order, and it is non-homogeneous. Why? Because on the right hand side you have the function. So let us find first is auxiliary equation. Okay, so that is m square minus 2m, okay, plus 1, okay, that is equal to 0. So since it is a quadratic equation, you will get 2 roots. Let us find those roots. So when I find this roots, so roots are real and it is also repeated, so that is 1 comma 1. So the complementary function, that is yc, will be c1 plus c2, now this will be z, okay, and multiplied by e to the power of z. Now we know what is z. Z is log x. Let us substitute it. So that is log x, I have substituted it, and e to the power of z is x. So on the right hand side what you get is in terms of x. So let us find the particular integral, that is yp. Okay, so that is 2z divided by, we have d1 square minus 2d1 plus 1. Okay. Now further simplification of this. Okay, so this is, now if I take and all separated, so I get this as entirely, let me put that as 1 plus this is d1 square minus 2d1. Okay, now if I bring it to the numerator, it is inverse, and 2z. Okay, let us further try to simplify this. So what do I get? So when I expand it, so I get 1 minus this is d1 square minus 2d1, fine, into, I don't require the other terms, so let us keep it like that. So because it goes to 0 when you multiply it, so higher orders is not required as of now. Let us multiply that. So what do I get? So I get this as, I have 2z, right? So 2z. So let us multiply. So I get 2z minus, now the differentiation twice, that becomes 0, and minus 2, and again differentiation of that is 2 again, so I get this. So the final answer which I get as 2z plus 4. This is your yp as of now. Let us substitute what we have taken earlier, that is 2 log x plus 4. Okay, so this is your yp. So y is equal to yc plus yp. So this is the solution of the differential equation. Let us look into another problem. Now let me write down. Let us write the differential equation. Now this is x square y double dash plus 2x y dash, right, minus 2y is equal to x plus 1 whole square. Okay, now again the same process which we have done in the previous problem. So this is x square d square into y plus 2x d into y, okay, minus 2 into y. This I can write as x square, let us expand this, x square plus 2x plus 1. Now if I take y as common, so I get x square d square plus 2x d minus 2 multiplied by y. So this is x square plus 2x plus 1. Fine. Further, if I take, let us put that is x is equal to e to the power of z, or log x is z, okay, and then afterwards let us substitute what is xd as d1, okay. So x square d square should be d1 into d1 minus 1. Okay, let us substitute all those things which I have mentioned. So that would be, now that is d1 into d1 minus 1 for x square d square, and for xd it is 2 times d1 minus 2 multiplied with y. So x square would be e to the power of 2z, and x would be, that is, e to the power of z, and we have the constant term which is 1. Now when I try to simplify this further, I get that as d1 square, this would be plus d1, okay, and minus 2 and multiplied by 9, so that would be equal to e to the power of 2z plus 2 e to the power of z plus 1. Now this being the second order differential equation and it is non-homogeneous, let us first find what is the auxiliary equation corresponding to this. So that would be m square plus m minus 2, which is equal to 0. So I get since it is a quadratic equation, I get two roots, that is minus 2 comma 1. Fine. Now let us find the complementary function, that is yc. So that would be e to the power of c1 e to the power of minus 2z, okay, plus c2 e to the power of z. Fine. Now in terms of x, let me substitute it, c1 x to the power of minus 2, okay, plus c2 into x. So the complementary function you got as that. So yp would be, now we have three particular integrals, z divided by, this is d1 square plus d1 minus 1, okay, and this is multiplied 2 and e to the power of z divided by, this is d1 square plus d1 minus 1, okay, plus 1 divided by, this is d1 square plus d1 minus 1. Fine. So we have to find these three particular integrals. Now let us find that. Now when we substitute d1 as 2 for the first one, so let us substitute that. So d1 as 2, let us substitute that. So first one would be that is 2 square, that is 4, okay. Now that is 2 and we have minus 2. Fine, for the first one. Now in the second case, let us substitute d1 as 1, let us substitute it. So actually this is 2 everywhere, right? Okay, make a correction of this everywhere. Okay, so let us substitute that. So I get this as this is 1 again, this is 1 again, and minus 2 and another 1. Now e to the power of 0 z, which is 1, so let us substitute that. So this would be 0 plus again 0 and minus 2. Fine. Now this is existing, so this is 1 by 4 e to the power of 2z, and if you notice this goes to 0. So what we have supposed to take the function of d, which is that is d1, right? d1 square, right? d1 square minus d1 and minus 2, right? So the derivative of this would be 2 d1 minus 1. Okay, so this should be multiplied with 2 and multiplied with z, and here you should have the denominator as 2 d1 minus 1. Fine, this is done. And the last term, which is minus 2, minus 1 by 2. Fine. Now further simplification of this. So this is the same, that is 1 by 4 e to the power of 2z. Okay, now let us put d1 as 1. If I substitute that, so I get 1 in the, now this is plus, right? So this is plus, so plus 1, and this is 3, you get 3. Okay, and the last term, which is half. So this is your yp. Now let us replace all the things so that we get yp as 1 by 4. So e to the power of 2z can be written as x square plus this would be 2 by 3 and z into e to the power of z. So you'll have log x multiplied with x, okay, and this is minus 1 by 2. So this is your yp. So y is equal to yc plus yp. So this will be the solution of the differential equation.